In this tutorial, we will be discussing the limiting reactant, theoretical yield, and percent yield. The limiting reactant is the reagent that actually limits the amount of the product that can be produced. The theoretical yield is the maximum amount that could possibly be produced, although it's never actually reached. So let's take a look at how we would determine the limiting reagent and the theoretical yield. So we have determined the limiting reagent and theoretical yield of the product if one starts with 1.20 moles of aluminum and 2.40 moles of iodine. Essentially what you're going to be doing here is two different lines of stoichiometry. You'll have one step going from iodine to Al-I3, and you'll have aluminum going to Al-I3. So you're going to have two different questions in the same problem. Remember, moles are the end caps of the horizontal line, and the coefficients are the conversion factors to go from one to the other. We talked about that in the previous tutorial. So let's start with aluminum. 1.20 moles of aluminum over 1. Moles of aluminum are on top, moles of aluminum will be on the bottom. We use the coefficients, and we're trying to get to Al-I3 to be both the same, so that way we can actually compare the two possible quantities. So 1.20 times 2 divided by 2, that comes out to be 1.20 moles of Al-I3. We're going to do the exact same thing for the iodine. So 2.40 moles of iodine over 1. Moles of iodine on top, so we're going to put moles of iodine on the bottom. The coefficient for iodine is 3. Then we're going to use 2 moles of Al-I3 on top, because that's the coefficient for Al-I3. So 2.40 times 2 divided by 3 comes out to be 1.60 moles. Now that both compounds are converted to the same product, we can actually compare them, 1.20 versus 1.60. The limiting reagent is going to produce the smaller amount. So that means aluminum is the limiting reagent, because it can never produce more than the 1.20 moles. And then this would be the theoretical yield, because out of all of it, that's the most it could possibly make. This is left unused. There's some amount there that's not going to be used in this process. Alright, so let's take this one step further. Since we don't measure out moles, we measure out grams when we go to the scale. So determining the limiting reagent and theoretical yield of the product that starts with 1.20 grams this time of aluminum and 2.40 grams of iodine. So 1.20 grams, we're going from here to here, we're going to convert them both to grams. Going from one compound to another, that takes coefficients, because that's the horizontal line. Moles are the end caps. So we need to go from grams to moles of this. That molar mass, after looking at the periodic table, is 26.98. From moles to grams, that molar mass, after looking at the periodic table, is 407.68. Remember, we're getting these numbers from the periodic table from adding aluminum and 3 iodine together. Now we're going to do, let's go ahead and do that real fast. So 1.20 grams of aluminum over 1. 26.98 grams of aluminum is in 1 mole of aluminum. Now we're here, and we're going to use the coefficients. So 2 moles of aluminum can yield 2 moles of aluminum iodide. And then from here, we can get the mass of aluminum iodide. 1 mole of aluminum iodide using the molar mass is 407.68 grams. that comes out to be 1.20 divided by 26.98 times 2 divided by 2 times 407.68 comes out to be 18.13 grams of aluminum iodide. Alright, so we're going to do the exact same steps for iodine. 2.40 grams of iodine. We're going from one compound to another, which means we're using coefficients. The moles are the end caps. And we're going up to grams. The molar mass of iodine is 253.38. That's 126.9 times 2. Oh, 253.8, sorry. Alright, so let's do this stoichiometry. We're starting off with 2.40 grams of iodine this time. Get from grams to moles, we use the molar mass, 253.8 grams of iodine is 1 mole of iodine. Use the coefficients, 3 moles of iodine yield 2 moles of Ali3. Then 1 mole of Ali3, and we're going to convert that over to grams by using the molar mass. So 2.4 divided by 253.8 times 2 divided by 3 times 407.68 comes out to be 2.57 grams of Ali3. Notice it's a smaller amount, so that means the iodine is a limiting reagent, and this is the theoretical yield. The second half of the question is how many grams of aluminum are left over. So what we have to do at this point is, since we know iodine is the limiting reagent, we need to convert iodine over to aluminum, going grams to moles, moles to moles, moles to grams. Scribble out this arrow so it doesn't confuse you. Alright, so I'm going to put it up here since I'm running out of room in the bottom. 2.40 grams of iodine. .8 grams of iodine on the bottom, 1 mole iodine on the top. We have it in moles now, so we can use the coefficients. 3 moles of iodine, 2 moles of aluminum are on top, and then for every 1 mole of aluminum, we have 26.98 grams. So 2.40 divided by 253.8 times 2 divided by 3 times 26.98 comes out to be 0.17 grams of aluminum that's actually used in this reaction. So how much do we have left over? 1.20 minus 0.17 comes out to be 1.03 grams. That was a really long, drawn-out problem. Alright, so let's try this again. Now we're starting off with grams of aluminum sulfide. So 15.00 grams of aluminum sulfide and 10.00 grams of water react until the limiting reagent is used up. What is the maximum mass of H2S that can be produced, that can be formed with these reagents? So we're going to do the exact same process. We're going from Al2S3 to H2S. Moles are the end caps, and coefficients always go over the horizontal line. Grams to moles, we use the molar mass. By looking at the periodic table, we find that the molar mass of Al2S is 150.17 grams is equal to 1 mole. And then H2S is 34.09 grams is equal to 1 mole. So we put this out over 1, 15.00 grams Al2S3 the molar mass is 150.17 grams of Al2S3, 1 mole of Al2S3, Then for every 1 mole of Al2S3 that reacts, 3 moles of H2S are formed. I found that out by using the coefficients. We're right here on our plan now. We have for every 1 mole of H2S that's formed, we produce 34.09 grams. So 15.00 divided by 150.17 times 3 divided by 1 times 34.09 comes out to be 10.22 grams of H2S. We're going to do the exact same process for water this time. We're going from water to H2S. Moles are the end caps. Coefficients go on the horizontal line. We need to go from grams to moles by using the molar mass off the periodic table. That's 18.02 grams is equal to 1 mole. I did that by adding 2 hydrogens and 1 oxygen together. And then the molar mass of H2S is still 34.09. Alright, so 10.00 grams of H2O. Got to get from grams to moles first. 18.02 grams of H2O are in 1 mole of H2O. For every 6 moles, because that's the coefficient of H2O that reacts, we produce 3 moles of H2S. And then finally, for every 1 mole of H2S we have, it's going to weigh 34.09 grams. That's going to come out to be 9.46 grams. This is the smaller amount, so that's going to be your theoretical yield. And this is going to come from H2O, which is our limiting reagent. Alright, so let's explore this a little bit more. We're going to talk about the percent yield now. So how much we actually produced when we were supposed to produce another amount. How much of the maximum did we actually produce? So theoretical yield, amount of the product that could potentially be made in a chemical reaction based on the amount of the limiting reactant. The actual yield, however, is the amount of the product actually produced by the chemical reaction. It's always less than the theoretical. The percent yield is the percentage of the theoretical that is actually produced. So here's our equation. It's the percent yield, the percentage of the theoretical yield that's actually produced. The actual is always on top, the theoretical is always on bottom. So this is what's made in lab. Well, this is what we could have been made. We could have made. And then you times it by 100 to get it into a percentage. So let's take a look at this. And the reaction of 20.7 grams of CaCO3 produces 6.81 grams of CaO. When it says it's produced, that means it's my actual. That's what we actually got when we were in lab. What's the percent yield? So we need to compare these two items. In order to do that, we need to convert one to the other. So moles are the end caps, coefficients. Grams to moles, we use the molar mass, which we can calculate off the periodic table by looking up all those numbers. We've done that several times before, so I'm not going to take the time to do that. Moles to grams. Once again, look on the periodic table, add up 1 calcium and 1 oxygen, you'll come out to be 56.08. Now we can put this into our equation. So 20.7 grams of CaCO3 we need to convert it to moles first, 100.09 grams. Now we can use our conversion or coefficients for every 1 mole of CaCO3 that's produced. we can make 1 mole of CaO. And now we're going to get it to grams. For every 1 mole of CaO, we can make 56.08 grams. So 20.7 divided by 100.09 times 56.08 come out to be 11.6. That is our theoretical yield. So it's going to be the actual, which is 6.81, over the theoretical, 11.6, times 100. That comes out to be 58.7%. Let's try this again. If the reaction of 91.3 grams of C3H6 produces 81% yield, how many grams of CO2? Because it's talking about the CO2, that's where I'm going to convert it to. And it's supposed to be 81.3%. We need to get from one to the other using the coefficients. Moles are the end caps. Grams to moles. Looking at the periodic table, 3 times 12.01, 6 times 1.01 comes out to be 42.09 grams per mole. 1 times 12.01 times 2, or plus 2 times 16.00 come out to be 44.01 grams per mole. Alright, so let's put our starting number over 1. 91.3 grams C3H6, 42.09 grams of C3H6, 1 mole C3H6, 2 moles for the coefficient C3H6 for every 6 moles of CO2 that are produced. Then for every 1 mole of CO2 that we make, we can have 44.01 grams of CO2. So 91.3 divided by 42.09 times 6 divided by 2 times 44.01 comes out to be 286.4 grams of CO2. Now 81.3% is what we actually got out of there. So x over 286.4 times 100 is equal to 81.3. So x over 286.4 is equal to 0.813. I divided it by 100. Now we're going to cross multiply that 286. We actually got 234 grams of CO2. We're going to have one final practice. A reaction of 0.112 grams of H2 produces 0.745 grams of H2O. What's the percent yield? Whenever you do the percent yield, you have to find the theoretical first. So we're going from one compound to another. Moles are the end caps. Coefficients. Grams to moles. We need to figure out the molar mass of H2. That's 2.02 grams per mole. Now we go from moles to grams. We had to figure out the molar mass of H2O. That's 18.02 grams per mole. So 0.112 grams of H2 over 1. 2.02 grams of H2 can get us into 1 mole of H2. So now we are into moles of H2. Now we can use the coefficients. We're right here in our plan. 4 moles of H2 for 4 moles of H2O. We're right here. Now we need to get into grams of H2O. For every 1 mole of H2O, we have 18.02 grams of H2O. So 0.112 divided by 2.02 times 4 divided by 4 times 18.02 comes out to be 0.999. Remember, in order to find the percent yield, you have to find the theoretical first, which is what this is. So to find the percent yield, is the actual 0.745 divided by 0.999 times 100. That comes out to be 74.6%. We have now gone over the actual yield, theoretical yield, and percent yield of stoichiometry in chemical equations.